So this unit, I'm going to call it Unit 5 because it's our 5th unit. However, it's all going to be from Chapter 7. Okay? And Chapter 7 is called the application of integration. So in Unit 2, we talked about derivatives. Unit 3 was the application of derivatives. Now that we've gone through our integration unit, we can talk about the applications of integration. Okay? Like I said, this is going to be today and tomorrow squished together. If we have school tomorrow, we'll have a work day on the 2 assignments. If we don't have school, you'll have a work day at home on the 2 assignments.
So either way, we're not doing math.
Tonight?
Yeah.
You can do it like that. Sure. Okay. You will want to get out your calculators. I'll just tell you that right now. There are going to be problems that I ask you to do by hand. There are going to be problems that I'll let you use the Math 9 command. However, I don't want us to use all of our integration skills, so there still will be problems I ask you to do by hand. But for today's notes, we're just going to do Math 9. Okay? Okay. So when we talk about the area from a curve to the x-axis, okay, this is what we did, right? We talked about our Riemann sum, right?
Yes.
And then when we take that limit of the sum of all of these itty-bitty rectangles, we're actually getting this, okay, where we have the height of our rectangles times the width, which ends up being height of our rectangles times the width, dx. Okay, so we're still taking the area of these rectangles. They're just infinitely many and infinitely small. Okay, now what we are going to do today is we are going to take the area between 2 curves. So instead of over here, curve to x-axis, we're going to talk about curve to curve. Okay. So, just don't write anything down quite yet. Okay. In green, if I take the integral from a to b of f of x, we would be finding this area here. Do you agree?
Yeah.
Thank you. If we find the area from a to b of g of x, we would be finding this right here. So what happens when you subtract those two? You get the area between curves. Okay? So what we can write is the area between curves would be the integral from a to b of f of x minus g of x, where f of x would be what we call our top function, and g of x would be what we call our bottom function. We want the highest minus the lowest, okay, in order to get that to come out to be a positive area. Okay. When we are talking about the area between curves, your area will always be positive, always, because we're talking about the area of a region. Okay. When we have area under the curve, or underneath the x-axis, excuse me, it is negative. Yes. But now, when we take area between 2 curves, it will be positive. Well, then that would be a different story. Okay. But we're always going to go in chronological order. Okay. So we don't have to worry. Okay. Now, the things that we're going to have to be careful with are where our region is. So if we don't have our calculator in our hands, we're going to have to draw our region based on a description. Okay. If our region is one where you have two curves and they intersect, you're going to have to figure out where those curves intersect. Things like that. But once you get your region drawn and you figure out where like that A and B are, you can just set up your integral and go. Okay? So a lot of today is just going to be examples, and then we'll look at what tomorrow's lesson would have been if we do our integrals in terms of y instead of x. Okay? So example number 1, go ahead and write down. Ooh. In this unit, every single problem needs a picture. In fact, on the quiz next week, whenever it is, I can't remember, you have it on your gold sheet. On your quiz, you get points for drawing a picture. Okay? Not just any picture. No. The correct picture. So here is x plus 6, right? That's the line x plus 6. You're okay with that? Okay. Some of you said, whoa, wasn't quite sure. Okay. Then we have the graph. Of y equals x squared. But then we only want it, and then we have x equals 0 and x equals 2. Okay? So we can kind of erase out the part of the picture that's not necessary anymore, like this right here. And this right here. Okay, that's our region. Okay. My piece of advice to you would be when you're drawing your picture, label your equation so you know which one is which. Now, in this one, it's pretty obvious. This is a line, y equals x plus 6, and this is a parabola, y equals x squared. But I might give you 2 parabolas, or I might give you 2 lines, or 2, who knows, a sine and a cosine. Make sure you label your equation so when you look at your picture, you can tell which functions are above versus below. So which function is our top function? X plus 6. Which function is our bottom function? X squared. What is happening is we are taking these infinitely small rectangles with thickness dx and we're adding them up together. So we have the integral. It begins at 0 and ends at 2 because that's what they gave us. Our rectangle height would be top function minus bottom function. So our top function you said was x plus 6 minus our bottom function was x squared, and those rectangles all have thickness dx. And by taking the integral, you're adding up all of those rectangles together. It's as simple as that. So, I know you can do the integration by hand, but I am going to ask that for the ease of notes today. Go ahead and just math 9 it for me.
Will there be times on the quiz where we have to do it like by hand?
Yes. So your first quiz will be half calculator, half non-calculator. Also, notice in your homework on the gold sheet where I specify which ones I want you to use no calculator on.
So if it doesn't say calculate,
Correct.
Is that little chunk like under the parabola where it says dx, is that also part of this?
No, so the only thing that I'm worried about, here, let me get my highlighter. We are only worried about this piece right here. Okay, and that's like the worst rectangle I've ever drawn in my life. Forgive me. Okay, what do we get for our area?
11.133.
I don't like that. What do you say?
34 thirds.
I like that better. Change it to a fraction if it's possible. If it's possible, it won't always be possible. I mean, no, I like it. Write this example down. Okay, so here I have the line y equals 2x, and I have the parabola y equals x squared, and I'm asking you to find the region enclosed by these two graphs. Well, when I say the region enclosed by these two graphs, I'm talking about whatever this is right here that's smushed in between. Okay? I don't get, like in that last example, I kind of gave you 0 to 2, right? Here we have to figure it out. Okay? So what are we going to have to find about these two graphs? Where do they intersect? Okay. Where does this guy intersect right here?
0, 0, 0, 0, and 2, 4.
Okay? Now, some of us were able to do that without any algebra. If it wasn't obvious, like in this problem, remember, you would set your two equations equal to each other, and then you would solve from there. Okay, so x equals 0 and x equals 2 would be our two places of intersection. That's where our integral needs to go from. All right? So, if I imagine these little rectangles with thickness dx sitting in here, we would have the integral we figured out from 0 to 2 of, what is our top function?
2x.
Minus our bottom function. Do you think this is a problem that I could put on a non-calculator portion of a quiz or test?
Yeah.
Taking this antiderivative and evaluating it from 0 to 2 is not beyond your capabilities. Okay? However, for today, use Math 9. Which is what? 4/3? Now I know me drawing in this rectangle looks a little silly to you because you think, what else would it look like? But here in a moment I am going to show you a way for us to find area in terms of y, in which our rectangles would look different. And then throughout our next couple sections, we're going to be finding volumes of revolution, where we take a region and we rotate it about an axis, and then our rectangles will be really important to visualize. Okay, so I'm just trying to get you in the habit now, before we get to the intense stuff. So here we go. Let's talk about these two regions. Go ahead and write them down. X equals y squared and y equals x minus 2. What does x equals y squared look like?
Yeah. How are we supposed to spell plus or minus?
What? How are we supposed to what? Okay. So the region enclosed by these graphs would be this guy right here, right? Now I don't know how accurate my graph is, but we'll go with it for right now. Okay. All right, so we probably need our intersection points, right? Okay, so where does x equals y squared and y equal x minus 2?
4, 2.
What?
4, 2.
How'd you find that?
Just kind of fell right.
You don't know? Okay. What else?
I don't know.
I don't know about 1, 1.
1
negative, that's right.
Okay. It's okay. Just had to
Come
make
on,
sure.
Grace.
Okay. Some of you are guessing and checking. Some of you are using legitimate algebra techniques. I don't really care. Okay? You're in calculus. Find a way to do it. Okay? Now, there is an issue. If we draw rectangles, with thickness dx, the top function and the bottom function of this rectangle, would they be the same as that rectangle right there? They would not. So what we're going to have to do is we are going to have to break this up into 2 different regions because our bottom function changes here. Okay? Now, if we're going to do this in terms of x, Mr. Altman right now is next door. If we're going to do this in terms of x, we actually have to solve for y. So what happens when we solve for y is we have y equals plus or minus radical x. So like this graph right here, and let me go ahead and just put it in blue. This blue piece right here would be y equals radical x, and then this green portion would be y equals negative radical x. Those two put together would be the x equals y squared. Do you see how that works? Okay. So, for our area, from 0 until 1, that blue graph is our top function, minus this green graph right here is our bottom function. But then, can I squeeze it in? From 1 to 4, we would have radical x minus x minus 2 dx. That didn't work at all. Just give me 1 second here. So from 1 to 4, radical x is our top function, minus x minus 2 is our bottom function. And we are subtracting the entire bottom function, so make sure it gets put in parentheses if it's more than one term, like in this case. Yeah.
One more time, how did you decide where the switch was?
So right here, our bottom function switches. So if I go from left to right, here the green function's on bottom, and then at this intersection point, the red function just becomes on bottom. Like if I draw a bunch of rectangles, right? I would stop at the green, but then after this coordinate, I stop at the red. Those are two different functions. Grace.
Does it matter that there's like a little triangle or like the root x part underneath the x-axis?
This?
No, the one to the like the little yellow, like you cut it in half.
Uh-huh.
on the right side.
Okay, so this triangle right here,
Yeah.
we're finding that when we take, because we begin at 1, and we're taking blue minus red, blue minus red, blue minus red. So we find all of that. Yeah. Other questions? Did anybody put it into their calculator?
I did. I got 21.
21?
Yeah.
Like on the dot, 21?
Well, 21. I mean, 0, 0, 0, 0, 0, 0.
Okay, so 21. How many of you find that annoying? That we had to split it up into 2?
I do.
I got a different number.
Oh no.
I got 4.5.
Ooh. I didn't get either.
Oh, I see my mistake. Yeah. I found my mistake.
Okay, so now you got 4.5?
Yeah.
Look what we can.
Nope. Sorry, I didn't.
Okay, like I said, that's got to go in parentheses, the x minus 2. Or you have to make it an x plus 2.
Ah. 1.
Okay, so good news. There is a better way to do this problem. If we were to create rectangles that stretched horizontally, would that be better for our integral?
Ah.
Yeah, because
I got it. Terrible. Not quite sure.
Uh-oh. Okay, so it is not always convenient for us to find those. However, what we can do is we can create rectangles that are horizontal, but this means they would have thickness dy. And our height of said rectangles would then have to be stretching horizontally. Okay? So if we take that same concept of top function minus bottom function, but now we're turning it sideways, we're now going to look at most right function minus left function in terms of y. Right minus left, top minus bottom. That's what you got to remember in this chapter. Can you do that?
Last one. That's where x equal to x minus 2 comes.
You'd have to square both sides.
Yeah.
Oh,
Yeah.
See, like, I feel like with this snow day tomorrow, I'm already clocked out of today.
I know.
It's terrible.
Would you like to try that example using y?
yes.
Let's. No?
I'm good.
I can use the black one to
What's the same example?
Where's the strategy? So the graph looks the same.
The graph looks the same. I just needed to redraw it. Same exact graph. Should our answer be the same?
Yeah.
Yes.
Yes.
Wait, really?
Yeah.
Should be.
That hurt my feelings.
Bless you.
Huh? What do you say?
You can still be
Sorry,
blessed.
I'm running out of
You can still be blessed.
air. Just hang with me here, guys. I don't have a lot of air in my lunch today.
Like, I think there should be a thing for cops.
People say bless you when you see it. When you see it,
Maybe excuse me.
what kind of disposed to work?
I don't know.
What to teach it? It's not a person.
It's definitely a blessing.
Everybody needs it.
So we have rectangles that are now horizontally, which means they are thickness dy, which means we're going to need our limits of integration to be in terms of y. Okay? So we already determined that these were 1, -1, and 4, 2. So now what's going to happen is for our area, we're going to go from y is -1 to 2 because our thickness is dy. Okay? And now we're going to talk about right function minus left function. Okay? So on the right, okay, and look at your rectangle. That can really help you see it. What's on the very right of our rectangle? Well, it's the line. Okay? Now, can we put in the line x minus 2? No, that doesn't make sense because we're in terms of y.
Y plus 2.
Okay, so what you're going to need to do is you're going to need to rearrange this to solve for x. So y plus 2 is your line minus your parabola y squared. Go ahead and put that into math.
Fluid.
Isn't that easier?
So
I just use
Sometimes it's nice to have multiple options on how to do a problem because one way is
you just
easier than
use
the
X
other.
anyway though.
Yeah, in your calculator, just use x's even though you have it written as y's. It's not going to make a difference.
Can you
Okay.
use the other variables to still work?
You can use the other variables, but it's going to be a lot more work for you to click like alpha y, alpha y, alpha y every time. I would just assume you do the X button. Okay.
Wait, you can use all these letters as variables?
Well, actually no. I take that back. You cannot use the other letters, but you can store numbers in those other letters.
That's fancy.
Okay. What do you get?
4.5.
What?
That is much easier.
I will probably give you a problem like that on the quiz where I say, do it in terms of x, do it in terms of y, you should get the same answer.
Actually, on my path,
Okay.
I don't understand.
Okay, draw your picture. I just want to see what you come up with before I tell you where it
What'd you say? Gross.
is. Excuse you.
Yeah, see, like,
Excuse you, go back to doing your math.
what you asked?
Draw it.
No.
They just turned the paper. I got a better one.
Okay, so when your functions are kind of like mixed around, I guess they're not really functions, your equations, where they're solved for x instead of y, our translations get kind of flip-flopped, okay? So typically, if this were y equals x minus 2 the quantity squared, it'd be a shift which way?
Right.
To the right. But since we've switched our variables, it's going to be a shift up.
Of course.
Okay? And this is going to be flipped, so it's going to open left instead of right. If this were y equals x squared plus 10, we would move it up 10, right? So since we're switching x and y, how about this way?
So it's total inversion.
Okay, so we're talking about this area right here. If we were doing this in terms of x, we would have to do 3 different integrals and add them together. Because the top function changes and the bottom function changes. However, if we do this in terms of y, the right function is consistent and the left function is consistent, so we would only need 1 integral. Now, we are going to have to figure out those limits of integration so we know how to set up our integral. Okay? How are we going to figure those out?
It's still equation.
X equals x. Okay, we're going to set our 2 equations equal to each other. We have quadratics. There's a reason why I have you in the specific seating arrangement that I do. I've been talking the whole time. Set it equal to 0. Then what would you do? Well, I would take the 2 out first because I don't really want to deal with it.
Yeah.
And then we can factor. Okay, so that was a lot of work, but now we know what our limits of integration are going to be. We know that we would need to go from -1 to 3. Those would be those values right here. Our function on the right, our equation, our graph on the right is -y squared plus 10 minus our equation on the left would be y minus 2, the quantity squared. Anyone get an answer? Lily? 64 thirds? Can anyone confirm or deny?
That's what I got.
Yeah?
I also got 64 thirds.
Okay. This is one that I probably would not make you integrate by hand, but your calculator isn't going to be a whole lot of help for the graph because you can't really type those equations into your y equals. Okay, so you'll just have to be careful. Real quick.
You could
Okay.
totally get the whole picture wrong and still get it.
Well, it's possible. So on the homework problems where I say no calculator, like I don't even want you to use your calculator to graph it, find intersections, anything. Okay? But there could be some times where you have to use your calculator to figure out your limits of integration. And I want to kind of just remind you how to do that. Here I have your equations. Y equals e to the negative x squared and negative sine of 3x. I hope you'd be able to figure out which one is which. But it's a calculator question, so you're going to have to graph it anyway. But in order to set up this problem, do those intersect at 1? No, you're going to have to figure out where they intersect. So I'm going to give you a moment to figure out where those two intersect, and I want you to set up your integral for the area of this graph. I'm not telling you dy or dx. You're going to have to figure that out. But what do you think? Do you want vertical or horizontal? Ooh, vertical, right? We'd only have to do one. So if we have vertical, we're talking about thickness dx. All right, find me that intersection and set up your integral.
That was really satisfying. The sign.
The graph.
Yeah.
I forgot what the intersection is. Make sure you're in radians because you're graphing a sine function.
First curve.
Oh yeah, those of you who are in stats. Oh yeah,
Does that just tell you?
Your guys is at 1.139.
When's that intersection then?
No, you do second calc.
Oh, so you're just.
I hit second trace and then went to number 5, which is 12. And then
So then, how
All right, what do we get for our intersection? What's our intersection?
on top of the sure I'm not trip.
Your intersection should be 1.139. There's multiple intersections, but that's the one that it's pointing to right there.
What is the most?
Oh, no.
What the?
You get 1.445, which is right there, answer B. Are you staying to take the other part too?
Yeah. Take it tomorrow.
Whenever I see you. Okay,
Oh.
how many assignments do you have? 2. You have today's and tomorrow's. Either we're here tomorrow and you have a work day,
Wait, that was like both?
or we're not here tomorrow. Yeah. I mean, I cut out some examples, but yeah, that's the basics.
Oh, were we just gonna do like top and bottom today? And
Yeah, tomorrow here's gonna do left minus right. Yep.
then,
Thank you, I appreciate that.
all right.